Today we're going to talk about vector-valued functions and their calculus. A vector-valued function is simply a function where the input is a number and the output is a vector. So for example, r of t is cos t, sine t, and t. Now we can visualize that as a curve. Now how would we do that? Well, r of 0, let's say, for example, is 1, 0, 0. So we would plot the point 1, 0, 0 right here. And then we keep going. So for example, r of pi over 2 would be 0, 1, pi over 2. So we would plot that point, not thinking of it as a vector, but thinking of it as a point. So what we're really doing is plotting the endpoints of each vector. And if we do that continuously, we're going to trace out a curve. Now you can use Calc 3D to visualize these vector-valued functions, and I'll just flip to that and show you. So what you'll do is go to select space curve r of t, and I'll just use the default here. And you can see there's this is called a helix, and you can animate and see the direction that the curve goes in. Okay, the domain of a vector-valued function is just the set of t's where all the component functions are defined. The component functions are the x function, the y function, and the z function. So if I call these f, g, h, let's find the domain of each function. For f of t, e to the 2t, the domain of that is all t. For g of t, we need t plus 2, the arguments, to be greater than or equal to 0. And so that implies t is greater than or equal to negative 2. And for h of t, again, we need the argument to be greater than or equal to 0. And that gives me, if I solve for t, t less than or equal to negative 1. Okay, so what is the intersection of these domains? Well, here's negative 2, and here's negative 1. G of t, the domain for g of t is all these t's going to infinity. But for h of t, it's these t's going from negative 1 down to negative infinity. So the intersection is this interval right here. So the domain is t between negative 2 and negative 1. Okay, parametric equations. We're just doing a little bit of preliminary material before we get to the calculus. Find a vector equation that parameterizes the curve of intersection of these two surfaces. Now on the next page, I have your parameterization Bible just for your easy reference. Now back up here, x equals y to the 5th, that's a function, so that's going to fall into this category, except instead of y equals f of x, it's x equals f of y. So in this case, we can parameterize x equals y to the 5th as letting y be t and x be f of t, which is t to the 5th. And we can just plug that into this equation. Z is 3x squared plus y squared. So that's 3 t to the 5th squared plus t squared, which is 3 t to the 10th plus t squared. So r of t, if we put everything together, x is t to the 5th, y is t, and z is 3t to the 10th plus t squared. Okay, let's jump to some calculus. The derivative of a vector-valued function is super easy. You just take the derivative of the component functions. And I've got a justification of this on the last page. So for example, if we want the tangent vector for this curve, we just take the derivative. R prime of t is 4t cubed, negative 4 e to the 2t, and then here I want to use the chain rule, bring out a negative 4, and then cos of negative 4t. Now you could have simplified this equation before you took the derivative, and since sine is odd, that would be negative sine of positive 4t, or you could leave it, and in this case what I did is I left it, but now I can clean up. This is 4t cubed, negative 4e to the 2t, and then since cosine is even, this is negative 4 cos of 4t. Now your homework's going to accept either one. Okay, related to that, find the unit tangent vector t of 0 for the exact same curve at t equals 0. So what we want here, big T of 0, unit tangent vector. So we want r prime of 0 divided by its length. Now we could find the length of r prime now and then plug in t equals 0, but it's a lot easier to first plug in 0. So r prime of 0 is 0, negative 4, and cosine of 0 is 1, so negative 4. So the length of r prime of 0 is the square root of -4 squared plus -4 squared, which is root 32. So t of 0 is the derivative, this vector here, divided by its length, root 32. So that's 0, -4 over root 32, -4 over root 32. Okay, so we typically graph the tangent vector on the curve and the position vector in standard position. So that's what this example is about here. Graph r of 1 in standard position and its derivative on the curve. So I've already found r of 1. So this is the function up here, r of t. You can double check my arithmetic. I found r of 1. I found r prime of t and r prime of 1. So we're going to graph r of 1 in standard position, meaning its base is at the origin, and I go to 1, 1. So that's r of 1. And now I graph the derivative on the curve, meaning I start here at 1, 1, and I go, for this guy, I'm going to go 1 over to the right and 4 up. So I go 1 over and 4 up, and this is now 2, 5, and you can see now r prime looks actually tangent to the curve, which it is. All right, so if you want more than a tangent vector, if you want a whole tangent line, that's super easy because the direction vector of a tangent line is simply the tangent vector. You compute r prime of t naught, and that'll be your direction vector, and your base point is r of t naught. And so here are our parametric equations for a line, and let's do an example. Let me erase this. First, I want x naught, y naught, z naught, and that's going to be r of pi over 4. Well, that's cosine of pi over 2, which is 0, sine of pi over 2, which is 1, and then ln of pi over 2. Now, that's a vector, but I'm thinking of it as a point, x naught, y naught, z naught. All right, and now I need my direction vector. So first start with the derivative, r prime of t. We're going to use the chain rule, -2 sine 2t to cos 2t, and then 1 over t. Now recall, for the derivative of ln of a function, ln of u of x prime is u prime over u. So what I did is I took the derivative of u, which is 2, over 2t, and that's how I got 1 over t. That's my scrap paper. Okay, now we need r prime of pi over 4, and that will be our ABC. So that will be -2, 0, 4 over pi. So that's my direction vector in the parametric equations for a line. So now I'm ready to use the formulas in that red box. X of t is x naught, which is 0, plus at. A is -2. So minus 2t. Y of t is y naught, which is 1, plus bt. B is 0, so just 1. And z of t, finally, is ln of pi over 2 plus 4 over pi times t. Okay, let's finish up with an integration problem. Just like with derivatives, we take the derivative of the component functions. With integrals, we take the integrals of the component functions. So for example, solve the IVP. We're given the derivative vector, and we're given it an initial condition. This is the IC. And we want to solve for r of t. So step 1 is to integrate to find r of t. And that's what I've started right here. R of t is the integral of the component function. So that gives us -1/2 e to the -2t plus a constant. And I'll call it C1 because I'm about to get another constant. And then when I integrate the second component function, I get ln of the absolute value of t plus 1 plus a constant C2. Step 2 is to find C1 and C2. So I'm going to use the initial condition. R of 0 is 1, 0. But it's also, if I take this vector here and put 0 in for t, I get -1/2 plus C1, comma, ln of 1 plus C2. But ln of 1 is 0, so just C2. All right, so that tells me that's two equations. 1 is -1/2 plus C1, and 0 is C2. So 0 is C2, and then C1 is 3/2. So step 3 is to put step 1 and step 2 together. So r of t is -1/2 e to the -2t plus C1. C1 is 3/2. And then ln absolute t plus 1 plus C2 but C2 is 0. And so there's our final answer. Okay, and you can read about properties of derivatives right here. And then that is the end of this section.